So yeah, as you can see, I want to talk about amenability and hyperfiniteness for group actions on trees, which is based on a joint work with these three co-authors, Sri Kunavalka Milayavalli, Koichi Oyakawa, and Forte Shinko. So let me just start with a bit of notation and introducing the question that I will actually be interested in. Maybe I'll bring this up a little bit. So in the whole talk, gamma will be a countable discrete group. And X will be some standard Borel space. So later in the talk, I will also have measures on here, but for now, it's just going to be a standard Borel space. Think of Cantor space or the unit interval or anything you like. And I will consider actions of gamma on X by Borel automorphisms. And the question will be, I guess maybe I put it a bit too high. So the general question, which I will make more specific in a moment, is when is the orbit equivalence relation hyperfinite? And let me explain in a few words what these things mean. So here E gamma X will be my notation for the orbit equivalence relation induced by this action, meaning that a pair XY is in this equivalence relation if and only if one is, well, they're in the same orbit, so there exists a G such as G of X is equal to Y. And hyperfinite means, so yeah, this means that as an equivalence relation, I can write this as an increasing union of equivalence relations with finite equivalence classes. So let me just, so increasing union of finite equivalence relations, meaning finite equivalence classes. Okay, and as probably many of you know, this is very much related to amenability, and it's very well known that in the measurable setting, when you put a measure on the space, hyperfiniteness, amenability, all these things are equivalent, and I will come back to those later. But for now, this is everywhere hyperfinite. Okay, and so I'm not just going to talk about any group acting on any space. So specifically, I want to consider group actions on trees and the actions that they induce on the boundary of those boundaries of those trees. So let me introduce those and then see what we can say about them. So our interest for today is gamma, which can still be any group, acting on the boundary of a tree. And so let me explain what I mean with this object. So first of all, T here is just going to be my countable tree. And so tree here just means a simple undirected graph with no loops. Right, so let me maybe here on the side to draw the only tree that I ever draw. Okay, that's actually not true. Sometimes I draw a binary tree. But this is one example of a tree, right? It is the Cayley graph of the free group, and the free group has a natural action on this, right? So that's a good example to keep in mind throughout, and I'll make some additional drawings on that side later on. In general, I'm not asking my tree to be locally finite, in fact. So I'm allowing, in general, vertices with countably many edges out of them, and so on. It just needs to be a countable tree. Okay, and so I want to introduce the boundary of this tree. And because I'm going to need it later on, I'm going to write down the specific, or one specific construction of the boundary of a tree, so that I can refer to it later. So let me first introduce one bit of terminology. So given a tree, a geodesic, which I will denote by sigma, because that's what we did in the paper, or respectively a geodesic ray, which we'll denote by boldface V, is, well, essentially just a path you can take in your tree. So precisely, it's an injective sequence of adjacent vertices, of subsequently adjacent vertices. And I guess I should have said maybe I'll write it like this, I forgot it, which is finite when I talk about geodesic and infinite for geodesic rays. Okay, so finite paths and infinite paths in your tree. Right, so for instance, you can have something like, I don't know, maybe you start at this point and then you just start running through the tree. This, for instance, is a geodesic, and then if you keep running off to infinity, it's a geodesic ray. Right? And because it's a tree, there's no circles, so essentially what you're doing is you're just walking around your tree. At every vertex, you just choose a new edge to run along, and you're not allowed to backtrack. That's all that's happening. Okay. And so maybe I'll write this up. Okay. So just for notation, I write sigma V like this to say that sigma is an initial segment of V. Sigma is an initial segment in initial segment. And so to define the boundary that I'm going to be interested in, well, intuitively, right, if you think of just a geodesic rays, you start at a point and you just keep wandering off to infinity. The boundary is all the points at infinity you can wander off to. Okay? And one way of defining that is the following. So one thing one can do is you can collect all the geodesic rays. So geo of t will be my notation for just the set of all geodesic rays. And then you can notice that you have a natural action of the natural numbers on geo of t by shifting. Okay? Namely, let's say the generator acts on a sequence v0, v1, v2, and so on by just removing the third vertex. Okay? So this induces an action of this monoid. It's not a group, but that's okay. And the boundary, so maybe let me specify it as a definition here. So delta t is just defined as the quotient space by this action. What does this mean? Because this is not a group action, I guess. But so, right, if you look at some different geodesic rays, let's also take orange, right? So I say that, so two are going to be equivalent. Maybe let's also start here, right? So for instance, I could have something like this, where like, you know, after this point, these two are the same, then these are equivalent for this action. Because I can just apply the action a few times here and a few times here to cut off some initial parts, and after that they're the same. Okay? So that's the equivalence relation induced by this monoid action, and the quotient is the also sometimes called Gromov boundary. Okay. Now in general, quotients by equivalence relations are terrible, but here this is actually a nice Borel space. One way of seeing this is you can identify this with just choosing your favorite vertex and identifying this with all the geodesic rays that start at that vertex. Right? It's a very easy exercise to see that every geodesic ray is equivalent to a unique geodesic starting at your favorite point, I don't know, like V0, say, or something. So this is a nice Borel space. And so it's that one that we will be interested in and that we will have groups acting on. Right? Because it's actually very easy to construct actions on this space, because whenever you have a group acting on your tree, it induces an action on the boundary. Right? Because if you have a group acting on the tree, you just act on all vertices, it commutes with this action, so it induces an action on here. Right? So maybe let me write that as an observation. if you have your gamma acting on T by just, graph automorphisms, then this induces an action on the boundary. Okay. By the way, if there's any questions at any point, feel free to interrupt me, of course, right? Okay, so now the question that I'm interested in, when can you deduce under certain conditions of actions on trees that this action on the boundary is hyperfinite or amenable or different versions that I will introduce later, okay? And a first result that we could show with my co-authors is the following theorem from last year. And it's a sufficient condition for the action of gamma on T for this to be hyperfinite. So if gamma acting on T satisfies the following, namely that for every geodesic ray, so for every geodesic ray, I can find some finite initial segment such that the stabilizer of V, meaning the group elements that stabilize every vertex that this ray goes through, is actually equal to the stabilizer of this finite initial segment. Okay. So if you just fix a sufficiently long finite initial part of your geodesic ray, then it implies that you will have to fix the whole geodesic ray. Okay. So if this holds, then we can show that then the action of gamma on delta T is hyperfinite. With which I, of course, mean the induced equivalence relation is hyperfinite. Okay. And so before giving a brief sketch of the proof, let me give a few new examples that this apply to. I mean, some specific cases were known before. And in fact, so maybe I should also say, we were certainly not the first people to be interested in this problem. There have been many people working on this. And in particular, the action of the free group, for instance, on its Cayley graph here, you can check that it is hyperfinite. This has already been known since the 90s. And mostly this has been generalized in the direction of hyperbolic groups, versions of hyperbolic groups, hyperbolic actions. Those are not actions on trees, but they're actions on some kind of hyperbolic spaces, and where you can also give a definition of the boundary. So in a sense, we restricted and generalized ourselves by only looking at actions on trees, which are nice as spaces, but allowing any type of actions of groups, and trying to find a general criterion, in this case, the one that I wrote down here, that implies hyperfiniteness.
But the action of F2 on the Cayley graph doesn't satisfy your criterion.
It does.
Then I don't understand because you're saying that the stabilizer of the a point at infinity.
No. So here I'm not saying a point at infinity. So this is purely a condition on the action on the tree itself. So G of T is the geodesic itself. So not the point at infinity. It's the geodesic.
It's the entire geodesic.
The entire geodesic. Yes.
Okay.
Yeah.
Thanks.
Yeah. No, but yeah, thanks for the question. It's good to point out. Yeah, so here with stabilizer of V, I mean, I'm just looking at V as a geodesic in the tree, and the whole geodesic is stabilized. Yeah. And we're actually going to use the proof of this in our proof, in a way. Yeah. But let me write down a few examples here. I'm not going to write them out in full detail, but just to give you an idea. So one concrete example, which is actually the one that we started from when we were looking at this, is amalgamated free products. So you write gamma as some amalgamated free product that acts on its bassarity. So there is a, given an amalgamated tree product, there's a canonical way of constructing a tree, a Basseret tree that it acts on. And so this satisfies the criterion when this subgroup K is so-called almost malnormal, meaning that for all G in gamma minus K, G, K, G inverse intersected with K is finite. Okay, so the group is not very normal at all. And the reason that, I mean, if you know about Basseret theory, then maybe you can see it, but otherwise you can always look it up later. But the reason that this condition implies the condition on the stabilizers over there is that in the action on this Basseret tree, stabilizers of edges are of this form, essentially, or of this form, like conjugates of the group K. And so this condition will imply that if you look at any segment of length at least 2, the stabilizer will be finite. But of course, the stabilizer of V is just an infinite intersection of the stabilizers of bigger and bigger initial segments. So if one of them is finite, then you have to have equality somewhere later on, because that's, yeah. So that's how this condition comes into play. So this is one example. Also, certain actions, maybe any acylindrical action. I'm not going to define what they are, but these are actions that people in geometric group theory are very interested in. And similarly, if you look up the definition of an acylindrical action, it's easy to see that they also imply that for big enough finite segments, stabilizers will be finite. And you do the same kind of argument as before. And so one particular example that I'm going to write down here is this applies, for instance, to, and let me be a bit vague, to certain natural actions of fundamental groups pi 1m for, and this is what was a closed orientable irreducible tree manifolds. If you know what that means, you probably know more about it than me. This example was pointed out to us by Dennis Olsen. If you have heard of this, so the action here is the action on the Basseret tree of the JSJ decomposition, which is apparently known to be acylindrical, and people have been studying these actions for a while. And so this theorem was actually not known for these actions, whether they always yielded hyperfinite equivalence relations. So yeah, so these are some examples in different directions that this applies to. Okay, but so let me give a very brief sketch of the proof before moving on to some more versions of amenability. So here, one way you can do this proof under a few small additional assumptions is by reducing the whole thing to Basseret theory and just working your way through and writing down on the nose that things are hyperfinite and so on. And we did that, and it's several pages long. And then we realized that that was the only condition we needed. And we wrote down a 2-paragraph proof. So that's the one I will give you. But maybe I should emphasize, the ideas really came from here, even though there is zero Basseret theory in the proof anymore. And the idea is this. So first of all, we look at these subsets of geodesic rays, which is all the, so for a fixed sigma, I look at the space of all V such that sigma is an initial segment and the stabilizers are the same. Okay, so by the assumption, the union over all sigma of geo sigma t is everything, because every V by assumption has an initial segment with the same stabilizer. Okay. But also, if I restrict my equivalence relations to these geosigma t's, they become very easy. So if I look at the equivalence relation of gamma acting on GOT, and I restrict it to the subset geosigma t, right, then what does this mean, right? Everything that I'm gonna have left is only the things that fix sigma. So this is now just the equivalence relation of the stabilizer of sigma acting on geosigma t. Okay. But by construction, right, this acts trivially here. So this is a very, very easy equivalence relation. Okay. And so because all of GOT can be covered by these, this is not a disjoint union, but you know that's not an issue. What you get is that the action of gamma on GOT will be smooth. But what that means for me in this talk is that the quotient is nice. So this actually implies that if you look at the quotient space of GOT by the action of gamma, this is a standard Borel space. And the reason you show this is that because this is covered by these easy things, you can easily find a Borel way of picking one point from each equivalence relation, from each equivalence class, sorry, which yields this. But now similar to the observation above there, right? The action of G and the action of N that I have over there, they commute, right? But now I have that this is a nice standard Borel space, and that action of N over here induces an action on here. And that is where we essentially use the proof of that theorem, because and in fact, so that was done by Doherty, Jackson, and Ketris in '94. What they tell you is that if you have an action of N, which is countable to 1, right? Because really the identity generator there is really just a countable to 1 function from the space to itself, then the equivalence relation it generates is always hyperfinite, okay? And I mean, you can look up their proof, it's very straightforward, but so this tells us that if I look at the action of N on G of T mod gamma, this is hyperfinite. Okay, because, yeah. But I claim that now we're essentially done. So now there is just one small lemma. Well, okay, that we include in the paper, but it's not like that this is crazy. So basically what we have now, we have the space G of T, both N and gamma act on it in such a way that the quotient space is standard Borel, and that will essentially allow us to swap these two, because they will both be isomorphic to just the action of gamma times N on G of T, right? Because these actions commute, so I can just define an action of the product, and then by the same lemma, you have that this is also the action of gamma on G of T mod N, but this is exactly the boundary, right? So this is exactly the one that I'm after. So.
Do you automatically get really isomorphisms, or rather
Sorry, I mean Borel bireducible. So isomorphic enough to preserve hyperfiniteness. Yeah. No, yeah, you're right. Yeah, but I don't want to define that here. No, they're not isomorphic in the strictest sense. You're right. But yeah, so that shows that under the condition I have over there, we get hyperfiniteness. Okay. Yes.
Can you tell me once more why the action of gamma on GOT is like 1? Like you said, it's smooth, right? Gamma.
Here? Yes. Oh, because I can cover GOT by subsets restricted to which it is smooth. Which means I can choose Borel transversals for all of these subsets, and then you just put them together by, you make a disjoint by just looking at the end one minus all the previous ones and putting together the transversals in that way. Yeah. Okay, so next I want to move to something a bit more maybe analytic. So this is basically as far as we could push the Borel hyperfiniteness. But as I kind of indicated before, right, measure hyperfiniteness is much easier, right? Once you have measures around, you can use Borel-Cantelli and other nice things to get measure zero sets that you then just kick out of the door and that you don't have to worry about. And so we could find some natural weakenings of this to get measure hyperfiniteness. In fact, when we started this, we were actually not aware of any actions on trees that yield actions on the boundary that are not measure hyperfinite. But it turns out that these do exist. I'll come back to that later. So you need some conditions in any case to get some kind of hyperfiniteness. But so yeah, maybe I'll write it here. So quick definition. So we say that an equivalence relation is measure hyperfinite. If for every probability measure on X, E gamma X is mu hyperfinite. Which as usual, I just mean you can find a measure one set so that when you restrict to it, you're hyperfinite. Yeah. Sorry?
You mean non-singular for gamma, right? The measure mu should be non-singular.
If you ask it for all measures, I don't think that's important. I mean, it will be, we will be applying it to those, but yeah. Sorry? Yeah, so the thing is, if you ask things for a specific measure, you have to be a bit careful, but if you ask it for all measures, you can...
What does mu hyperfinite mean?
So, you choose. So either it means that you have a gamma invariant measure one set restricted to which you're hyperfinite, or you don't require gamma invariant. For a single mu, this makes a difference, but for all mu, it doesn't. Because then you just go to you take it in a sum of some measures, and you can always make it invariant. So that's why I'm not being too precise about it. But feel free to assume that you have a measure one gamma invariant subset. Okay, and so let me introduce one more or two more definitions here that are very similar to things that probably many of you are familiar with. But are the conditions that we kind of could use in order to generalize this approach. So if you have gamma acting on any set A, so A here is now just a set. It will be some countable set in general for us. And you fix a finite subset of gamma and some positive epsilon, then an S comma epsilon rider function, rider function.
Excuse me, because
Yes.
I'm still trying to understand.
Yes.
Does it then mean that it's measure hyperfinite if it's hyperfinite restricted to any Borel set, so that the complement can have measure zero for just a measure?
Yes.
Okay.
Yes.
So you define sets to be small if they are Borel and measure zero for just a measure.
Yes.
Okay.
Yeah. I mean, often we're going to be interested, of course.
Sure. Yeah, there exists a measure for which is measure zero, and then you call it small. Or
Oh, no. So what yours? Yeah, sorry. right, what I'm saying is for every measure, there exists some measure zero set that you can throw out. Right, I'm not saying that for every measure, any measure zero, right? Any measure zero set, right? Yeah, yeah.
That
Yeah.
you take out this set, it is more.
Yeah, yeah. Mm-hmm.
Okay.
Yes, exactly, yeah.
So then given a measure that exists a set,
Yes,
depending on the measure, such a restriction.
exactly, yes.
Thank you.
Okay. Yes, so let's see. Yeah. So these S epsilon rider functions for an action on a set are probability measures on gamma. So is some probability measure on the group gamma such that the push forwards somehow are invariant. So for any S in my finite set and for any A in my set A that I'm acting on, if I look at the push forward measure on the orbit of A and the push forward measure on the orbit or on SA, so shift the measure on the orbit, then in one norm this is less than epsilon, where just probability measures on a set A, I just identify as a subset of positive elements of L1 of A, right? So that's my L1 norm. Okay. And this is, of course, very similar to today's criterion for amenability of countable groups, right? Which is where the motivation comes from. And so we define a subgroup of gamma to be uniformly coamenable if these things exist for the action of gamma on the cosets. So if gamma on the cosets has S epsilon rider functions for all S and epsilon as in the definition. Okay. And it's closely related to the usual notion of coamenability, but it's, at least, I mean, we don't know if it's equivalent. We couldn't really quite figure it out. So examples are certainly, if gamma is amenable, or if this is a normal subgroup so that the quotient is amenable. And so we called it uniformly coamenable because it's kind of like you get these probability measures on gamma, like one on gamma that you can push forward to these quotient spaces. Okay, and so the easy lemma that one can show, maybe let me start erasing some things.
But it's not even clear that it applies to amenability.
No, it's just different,
So
yeah.
then the adverb uniformly is kind of confusing.
Yeah, if I'm open to suggestions for better terminology. Maybe uniformly similar to coamenable or something. Okay, but so here is a lemma. So if you have an action of gamma on some standard Borel space X, which satisfies that every stabilizer of points for this action, every stabilizer is uniformly coamenable in gamma, then what I claim is if you then look at the orbit equivalence relation for this, E gamma of X, it is, I guess, Borel amenable. which I will tell you what I mean by that.
Does that hypothesis mean anything else than just for the action of gamma on X you have as epsilon right functions?
Wait, actually, is it?
Seems to be linked at least, maybe the quantifiers are different.
Certainly one of the directions. Yeah, maybe it is just this for X.
Ah, but there it's even uniform in A.
Yeah. Here it's uniform in A. Oh, yeah. So no, it doesn't mean. Yeah. Sorry. Yeah, I was a bit confused when I was there. Yeah. So here it is for all A. So this technically, like, we usually do this for countable sets. Yeah. Okay, that's good because, like, for a moment I was thinking that we did some unnecessary stuff. Okay. So, and here with Borel amenable, well, I just mean the
X is what?
sorry?
X is?
X is some standard Borel space at this point. I mean, in a minute it's going to be the boundary of a tree again. And so here it's the Borel version where you don't throw away measure zero sets of the usual amenability for equivalence relations. But so let me write it. So it means that there exists, this is at least one of the ways of writing it. There exists probability measures on equivalence classes. So with this I mean the equivalence class of some point X. So there's this probability measures for all, so for I in N, X in X, such that whenever I take 2 points in the same orbit, these probability measures are asymptotically the same. So in the one norm PIX minus PIY, in one norm goes to 0. Where again here, these are both just equivalent probability measures on the equivalence class of X, which is just a countable set. And so that's where the L1 norm comes from. Okay. And once you just look at this definition and this definition long enough, then it's very easy to show that you can just push forward the measures you get from these stabilizers onto the orbits and you get that. So this is certainly not the difficult part. Okay. And so essentially what Kohn, Feldman, and Weiss did in the 80s is showing that measure amenability, or mu amenability for a measure mu, say, is the same as mu hyperfiniteness. Okay. So if you can show, but it is not known if Borel amenable implies Borel hyperfinite. Okay. But in any case, if you can show that a certain equivalence relation is Borel amenable, then certainly it's measure hyperfinite because of the Kohn, Feldman, Weiss. Okay. We will not quite do that later, but I'll indicate in the proof. But the theorem, at least, can be nicely stated, so it will be similar to the one over there. Namely, so if gamma on T satisfies that for every geodesic ray, there exists some initial segment such that the stabilizer of V is uniformly co-amenable in the stabilizer of sigma, then the action of gamma on the boundary of T is measure hyperfinite. Okay, so I mean, from the things I've said here, maybe it's hopefully not that surprising, But let me, indicate the proof. So I think I still have the sketch of the proof here. So let me just bring this up. So let me not write too much. And just look at the proof of the original one. So we start off the same. Instead of, we define geosigma t not like this, but we're saying that this inclusion is uniformly co-amenable. Okay. Now you need a little argument that these are Borel sets, but that's not too difficult, also relying on the lemma that I have up there. So you still get a cover of Geo of t by these sets. Okay, now this action of the stabilizer here, it's not trivial anymore, but it is Borel amenable by the lemma that I have. So this is Borel amenable by our lemma and the assumptions. Okay. So, and now let me erase something, because so we can certainly not deduce this anymore. But again, similarly, by just putting together these pieces, it's again very easy to show that this implies that the action of gamma on the geodesic rays is Borel amenable. And now we want to again kind of understand what this induced action of n is doing, right? It's not acting on the quotient space anymore, but I still have an action of gamma times n. That is fine. And all we add is accountable to one function. And so then there is a nice paper by Jackson, Kechris, and Louveau from 2004, I think, or 2002. They tell you that if I now look at the action of gamma times n on Geo of t, unfortunately it's not Borel amenable, or we don't know if it's Borel amenable, but it is Borel 2 amenable. And this is where I learned that descriptive set theorists have this whole hierarchy of alpha amenable for alpha countable ordinal. And hyperfiniteness implies amenable, implies 2 amenable, implies 3 amenable, and so on. And it's not known whether they're all equivalent or all different. It's probably one of those two, but who knows? And so, but it is still known that that all the alpha amenables in the measurable setting are just all the same.
And does it have just to do with the degree of measurability of your maps to L1? Or?
No, so if you think about Borel amenable, so I have the definition up there, right? So I have this convergence of the PIs. So for Borel 2 amenable, we get a Pij axis with 2 indices, and we get convergence along n times n, along a filter, which you get as the tensor product of the cofinite filter with itself. So the being alpha amenable for some countable ordinal alpha is also called Fréchet amenable, because you get these, like, you start with the Fréchet filter, and you kind of get like weaker notions of convergence. That you can define. You can also write it down with epsilons and deltas and so on. But yeah, for 2 amenable, you get Pxij with 2 indices that converges to 0 along some filter on n times n, which is a weaker notion than that one. It was entirely built to try and attack Borel hyperfiniteness, and it is not known whether they're all equivalent. But it is known, and we have an argument in the paper as well that concretely works this out, that this implies measure hyperfiniteness. this is actually not too difficult, but once you know what you're doing, there's some very funny results as usual in the literature about this, where the first thing that was shown was that under the continuum hypothesis, this implies measure hyperfiniteness and things like that. But yeah, so I mean, if we forget for now about the 2 here, then essentially it's a version of amenability which by a similar argument and idea as the Kohn-Feldman-Wise implies measure hyperfiniteness. And so that's where we can finish the proof of the second theorem I wrote up there.
And so am I right? Then all these levels of amenability imply that there just exists a net BIX.
Yes.
Okay.
Yeah. Exactly. Yeah, so well, this is roughly as far as we could, and of course, right, again, if you have an amenable group acting, you get that there are, like, all the actions are Borel amenable and 2 amenable and so on. Just the hyperfiniteness is the one missing link. Okay, so I have a few more minutes, unless there are other questions about this. I want to say a few words about the fact that one needs some conditions, and there exist actions for which on trees for which the action on the boundary is not hyperfinite. So maybe let me erase my wonderful picture. Oh, actually, I don't have to. So here's the fact. Right? So, and as I mentioned, when we started on this, we were not sure if these actions existed, but as many things in the theory of countable Borel equivalence relations, Alekos-Kekres already knew about this since the dawn of time. And so, but the construction is actually very easy. So if gamma is any residually finite group, then there exists an action of gamma on a tree, which is in fact rooted, so it fixes a point in your tree. Such that, and a measure on the boundary of T, such that the action of gamma on the boundary of T is free, essentially free, and measure preserving. And the way you do this, you take your sequence of decreasing normal finite index subgroups, and you somehow build your action as an inverse limit of actions on countable sets, and you can get this. It's a relatively straightforward construction. But for instance, if you apply this to the free group, right, you get a free measure preserving action on the boundary, so it cannot be measure hyperfinite, right? So certainly for any non-amenable residually finite group, it's very easy to construct actions on trees so that the induced action on the boundary is not measure hyperfinite. And yeah, but so to what extent these conditions can be weakened or adjusted is not entirely clear. But so that is where we stood when we finished the paper. So that's all I wanted to say. Thank you so much.